Hello everyone, you are welcome to this channel. Today we shall be looking at another technique that that can be used to solve difficult polynomial equations. And that is basically numerical method. Numerical method. When we talk about numerical method, we have been used to solving different equations to find their root or to find any value of interest. But at times we encounter difficult equation. Like the common quadratic equation that we have y is equal to x squared minus 2x plus 3, we often need to find the root. And what is the root? Root is the point where the curve cut the x-axis. So like the curve cut the x-axis here, it cut another here. So there are two roots here. So we look for the two in solving quadratic equation root. So basically, we are looking for when the point y equals to 0. That is where the root lies. When the point y equals to 0. So as a result to solve it, we say x squared minus 2x plus 3 equals to 0. Because that is the point where our y equals to 0. We are looking for that root. It is easier to solve for quadratic equation because there are standard methods like factorization, like almighty formula and so on. But when we encounter higher power polynomial like x squared minus 3x plus 5, y equals to that, then we are dealing with three roots. And there are no very easy formula that is available like that for quadratic. So there are three roots here because it cut the x-axis at 3 points. So the idea is to first of all get the first root and use that to reduce it to the quadratic format. So we have to guess. When we are guessing, we realize it's wrong. Then we have to move to the next step to guess another point. To guess another point until we are close to the actual root. So the method we are going to be demonstrating in this work, in this tutorial, is fixed point iteration as well as Rapshon. Let's look at fixed point. It is used to find approximate solution to tedious algebraic and transcendental equations. And the idea is that it creates a fixed point in a domain of a function g such that gs equals to x. The principle is that it converts the original equation into a function gx where the gx and x are equal. So it now uses that basis to calculate the actual value whereby it keeps moving until it crosses the point of equality. So there are some steps to follow when doing this. The first is to determine the initial guess. We have to make initial reasonable guess. So how do we do that? We have to look at the curve and see how we have to look at the curve, like the curve here. Let's assume this is the curve. So though we are not sure. So we have to look at the curve and see that we take a value to the left and to the right. We guess a value to the left and to the right so that we'll be sure that the root lies in between. And how do we now do that here? We choose a value, we substitute into the original function, and we see if it is less than 0. Then we choose another value and we substitute the original function and see if it is greater than 0, so that we know that the root lies in between the two. The second step is to convert the function algebraically to the form gx equals to x. Now, there are many ways to do the conversion, but whichever way we choose, we have to test whether it satisfies this condition, g prime x absolute less than 1. That is, we differentiate the conversion we have done and see when we substitute the original guess here, if the value is less than 1. If it's not less than 1, we have to discard it and choose another conversion. So after we have satisfied the second step, then we move to the third step to perform the iteration. Let's look at this example. Find the approximate root of 2x cubed minus 2x minus 5 equals to 0. Now, let's try to solve this. To solve this, we follow the three steps mentioned. The first step, initial guess. and we have to apply the condition. So if we assume that x is equal to 0, our f of 4 will become 2 into this. 2 times 0 cubed minus 2 times 0 minus 5, which gives us minus 5, which is to the left. Then we assume next x is equal to 1, f of 1, 2 times 1 cubed minus 2 times 1 minus 5 equals to minus 5, which is also to the left. Between are negative. So that means we still need to move forward. Then x equal to 2, f2, 2 cubed minus 2 times 2 minus 5 equals to 7. So we can see that this one is positive. That means our root lies between x is equal to 1 and x is equal to 2. It lies between x is equal to 1 and x is equal to 2. So that gives us a guide and makes our, so we cannot choose x naught to be 1.5, which is the halfway between 1 and 2. We can choose 1, we can choose 2, but it's good to go midway so that you can easily approach the root easily. So the next step is to find the second step, which is what? To convert algebraically. The second step, convert the function algebraically so that gx is equal to x, equals to x. So look at the function 2x cubed minus 2x minus 5 equals to 0. We can calculate from here. Let's do the first one, the first option. Let's start from here. 2x cubed is equal to 2x plus 5, and our x is equal to 2x plus 5 divided by 2, everything raised to power 1/3. So we have chosen this, but we have to test. You remember the test we need to perform, that does it satisfy the differential of x less than 1? So let's try to substitute that. So g prime, so this is g of x now that we have chosen. Now g prime of x equals to what? We differentiate it, which is 1/3, multiplied by 2. Then we have 2x plus 5 all over 2, everything raised to power minus 2/3. When you differentiate, you are going to get that. So when you substitute the x naught is equal to 1.5 that we got in the first step, you are going to see that the value of this gx is less than 1. So that means we have satisfied. If you try it in another way, which is 2x here, which is b, 2x is equal to 2x cubed minus 5, and so that is 2x is equal to 2x cubed minus 5, and our x is equal to 2x cubed minus 5 divided by 2. When you substitute this, our new gx now, when you differentiate that and you substitute the x naught, you will realize that our absolute is greater than 1. So which doesn't satisfy our condition. So therefore, we go for this option. So, and that is what we use. That's our gx, 2x plus 5 over 2. So the last step now is to perform the iteration. So let's perform the iteration. So the step 3 is to perform the iteration. So we have our n1, the first step. N means step now. Our x naught is 1.5. So we need to calculate our x1, which is what? From the equation, we have 2x plus 5 over 2 raised to power 1 over 3. So x1 is equal to 2 times 1.5 plus 5 divided by 2 plus 5 divided by 2 raised to power 1 over 3. When you calculate that, that will give us 1.5874. So now we take the second step by substituting that our x1 is now 1.5874. So we use that to calculate our x2. So 2 times 1.5874 plus 5 divided by 2 raised to power 1/3. That will give us 1.5989. So then we continue. The third step to get our x2 is 1.5989. Let's use that to get our x3. So 2 times 1.5989 plus 5 divided by 2. Then that gives us 1.6300. So in the long run, we have this first step, second step, third step, fourth step. So you can see it has started converging at the step 4, 1.6037, 1.6057. So with that, by the time we try go to step 5, we see that things have converged, and we can say that our root is at x4 or x5, which is 1.60057. So that is that for the fixed point iteration. Let's look at the Raphson method. The Raphson method also follows similar approach, and what it does is that looking for root, it comes to it to suggest, it guesses here, and once it tests, it will try to find what is the function point there. It traces the initial guess to the function call and draw a tangent. When it draws a tangent, it uses that tangent where it crosses the x-axis to find the next point. So this one will be our x0, this one will be x1. Once it tests it that it doesn't satisfy again, it will trace it back to the curve and still again draw the tangent to get. So you can see that it's approaching the root gradually. So that is it. So the formula is that to find the next x, xn plus 1 is equal to the last x that you've got minus the function at that point xn all over the differential of the function at that point xn f prime. So that is the procedure. So the steps are also 3. You initial guess, just like the fixed point iteration. You compute the end out term. What are the end out term? The fx and the f prime x, the differential. So then the last step is to perform the iteration. So it's much similar to the fixed point iteration procedure. Now let's see the same equation that we solve for the fixed point iteration. Let's solve it now for the Raphson to find the approximate root. So initial guess, step 1, initial guess. Just like the Raphson, we say we find at x is equal to 0. So we find f naught. Just like before, we got minus 5. X equal to 1, we find f is equal to 1, we got minus 5 again. Just like before. Then we at x equal to 2, f is equal to 2 into the equation. We got 7. So which means just like before, it is between 1 and 2. So we can choose initial to be. So this is just exactly the same like the fixed point iteration. So the second step is to now. So the second step is to compute the Raphson term. So the second step, Raphson terms. So you remember the equation is 2x cubed minus 2x minus 5 equals to 0. So and the Raphson term, to get xn plus 1 is equal to xn minus function of xn all over f prime of xn. So to compute this term, function of xn is the same thing as the equation. So function of xn is equal to 2x cubed minus 2x minus 5. And function prime, f prime, which is the differential, will be equal to 6x squared minus 2. So let's now go to the third step, which is to iterate. So when n is equal to 1, remember our initial guess is 1.5. Therefore, to calculate our x1, it will be equal to xn, which is x0 now, 1.5 minus function of xn, which is this equation, and that will be 2 times 1.5 cube minus 2 times 1.5 minus 5 divided by f prime x, which is what? 6 times 1.5 square minus 2. So when you compute that, x1 will give us 1.6087. So let's see for other step, n is equal to 2. Our x1 now is now equal to 1.6087, and therefore to calculate our x2 from there, we get 1.6087 minus 2 times 1.6087 cube minus 2 times 1.6087 minus 5 divided by 6x square, 6 times 1.6087 square minus 2. So when we compute that, we are going to get x2 equals to 1.664. So if you continue like that, we are going to have this kind of iteration. So in the Raphson, from the first step, second step, it has started converging. By third step, it has converged. So it has converged with the second step. But when we look at the fixed point, it's 1.58, 1.59, third step, fourth step before it converges with the third step. So it means Raphson converges faster than the fixed point method. So Raphson is a better method in this regard. So thank you very much for listening. If you have any comment, kindly post it at the comment section, and remember to kindly subscribe to this channel. Thank you.